I'd always beware of eating anything from the chem lab. It's a shame. All right, so in our discussion of rotational motion, we've covered our chapter 2 equations. We've talked about forces. We are not going to talk about momentum yet because that's one of those really funky things. So we're going to talk about that later. But it leaves us with energy. So, what does the work kinetic energy theorem tell us? Which is what? Okay, so work is equal to the change in kinetic energy, K final minus K initial, in whatever form it's in. But we also had another way to express work, right? What was the work done by a variable force? Qu'est-ce que c'est? No, it was not 1/2 kV squared. And you may be thinking of a spring, which is a particular variable force, but I want to know in F dot D only works if, under what circumstance? If F is a constant. So what's my general formula? What? F of x dx from some initial x to some final x. And then when F is a constant, this reduces to work is equal to F dot D. And we had one more thing that we talked about in terms of energy, and that was power. And what was power equal to? Okay, so if we're going to go all calculus on it then, it's dW dt. And we had another formula for power. No, we did talk about it as being dE dt at some point, but that really has to do with the work as well. But there was a different way that doesn't look like this that we had to talk about power. What is it, Sari? And it wasn't just FV, it was F dot V, right? Okay. So all of these things that we have up here, F's and V's and X's, and really we could rewrite our kinetic energies here as 1/2 mv final squared minus 1/2 mv initial squared. So for the V's and the M's and all that stuff, we have rotational values, rotational analogies to these that we can use. So let's see what we got. Okay, if we consider a single particle, M, rotating due to a force, F, at a distance, R, from the rotational axis, then we can say some stuff. All right, so everybody got that part written down? Who's writing it? All right. So if I look at the change in kinetic energy of that particle, first of all, is the particle's velocity and therefore kinetic energy going to change? Well, what about this? Forces cause what? Accelerations. So yeah, it probably should change. Okay? So I could talk about some final kinetic energy minus some initial kinetic energy. And that would be equal to the work done. But remember, I'm trying to turn this into rotational stuff. So if I have a tangential velocity, which is what these V initial and V finals are, then I've also got a what other kind of velocity? A rotating velocity, an angular velocity. And what's the symbol I use for angular velocity? No, omega. And how are omega and V related? Think about the units, okay? What are the units of V? Meters per second. What are the units of R? What are the units of omega? Radians per second. Remember that the radians go away. So the meters per second, meters per second. Okay? I'm going to substitute those in. So now I've got 1/2 m. My r is going to be the same, right? Because it's rotating that distance out from the center and it doesn't move. So I've got r squared, and then I've got omega final squared minus 1/2 m r squared omega initial squared. And this would be a really good time to note that you must make your W's for work and your omegas for angular velocity look different. Which I've been telling you for weeks now. I think it does look like a butt. All right. However, what's mr squared? Yeah, it's rotational inertia. Okay, so you have a question? Okay. It's rotational inertia for a single particle. Okay, but if eventually I'm going to think about a whole system of particles, yeah, I can say that delta K is going to be 1/2 I omega final squared minus 1/2 I omega initial squared, which is going to look like, or which is also going to be equal to the work. And that's kind of, if I asked you before we started what you might want rotational kinetic energy to be equal to, you'd probably say 1/2 I omega squared, right? So this is, again, only going to work for rigidly rotating objects. So that was one of our formulas. That was when the work is due to a change in kinetic energy. But what if instead we'd want to talk about the work done by a force? So I'm getting there. That's whoever said that. That was a good idea. Okay, so I'm going to consider some particle I have out here that's rotating, moving around a circle at a distance r from the rotational axis. And there's some force F on it. I know. And I don't know why it has to be that loud. It is like right by the wall, and so that's why closing the door. But let's think back to freshman physics, shall we? Because everybody had freshman physics, right? Right? Okay. Many of you had it with me. So the wall is what kind of an object? Liquid, gas, solid? Solid. How does through which medium does sound transmit the best? Gas, liquid, solid. I know Mrs. Leas did this with you guys. How is sound transmitted? Yeah, what kind of a wave is a sound wave? No, it is not a wave that looks like this. That's a transverse wave, and that is not a sound wave. I'm oh so proud. It's a longitudinal wave. At this point, I haven't done freshman physics in almost 3 years, too. All right. I didn't teach it last year. No, the kids after you. No, Isabel Finkbeiner and Zoe Knaus from my last class. But, so remember that a longitudinal wave, it's got to move. The particle gets excited and it vibrates, and it has to hit the next particle, and it has to hit the next particle. So in solids, the particles are closer together. So the sound wave is going to travel better through the solid because in that distance between the particles, it's not losing energy by vibrating for no good reason. Yes. Okay, so even though the speaker is going that way, there's probably some sound that's coming out of the back of the system, but because it's traveling through the wall. And that's why we find that closing the door doesn't help. It would still transmit better than through air because the particles are closer together in liquid. There would just have to be no wall and it could be air. Yeah. There'll be some damping, but that's... You're not, well, first of all, there's an amplitude issue. Okay, and please don't yell really loud. Okay, so please let's not do that. There's also, didn't we do this with you guys? Maybe we did. No. Well, it's more that if you, well, the point I wanted to make is when Priya was trying to talk through the table, okay, first of all, the table is made out of something different than the wall. Second of all, the table is smaller than the wall. So did we do the thing with you? I can't remember because I don't know where it is anymore. Where you take a tiny little music box and you play the music box. and then you put it on, maybe it was a video and I didn't show it to you, and then you put it on like a box, and you make the music box go, and now you can hear it. And the music box hasn't changed itself, but the box vibrates too, and so that makes the sound bigger. So the table is a little bit different than this whole wall acting. It may. Sure, Priya. Go ahead. Just don't really write on the door. I mean, you can scratch on the door anywhere you want, just don't write on the door. Okay, so now do the same thing, make the sounds the same way with the door open. It was louder when the door was shut. That not so much, but the scratch was definitely louder when the door was shut. Science. It's waves. We could do levers after we should definitely do levers. We could do simple machines after. Well, because we ran out of time. Because I often do it. But yeah, but I've been trying to figure out what we're going to do after the AP exam, so we could definitely do simple machines and do some more stuff with pulleys too and stuff. We can do that. Well, we're definitely going to do Maddie's hair. I mean, that's like a given. Try to find the steering constant of Maddie's curls. It was her idea. I'm actually really good with that too. Well, you have to have Mariah's permission to do that. Okay, so think about that in your spare time. If there's something that you want to personally explore, I'll come up with some kind of form and you can fill in the blanks. Okay. That's fine, Priya. I'm good with that. As long as it involves some kind of physics, I'm good. And if you can't come up with an idea on your own, I will come up with something for simple machines. It is. Okay, so let's do what we got to do, though, because I want to be done with this chapter today. And I feel we can do it. All right? So I've got my particle that's moving around in a circle. Okay? It has a force. But of course, I can break that force into a tangential component and a radial component. And as the particle moves some ds, so some really small distance, okay, a differential, around the circle, only the tangential component of the velocity acts, matters, whatever you want to do, however you want to call it. Okay. Yeah, just changing the direction. Okay. So this does work, because remember, the whole thing about work is that the force has to be parallel to the direction that the work is done in. Okay, and when we talk about it, where were we? When we talk about it this way, note that the force is a function of x, and we're integrating it in the x direction. So we have taken an incredibly simple way of looking at this. All right? If you take physics classes, higher order physics classes later on, you'll learn different things about it. Okay? But if I want to talk about the amount of work done by that force, I can only talk about the component of the force that's parallel to the direction my particle's moving. Okay. But of course, I'm talking about rotational motion. So I don't really want to talk about ds. How do I talk about distances when I'm talking about rotational motion? Theta. So, flashback, how are s and theta related? Okay, doesn't matter how you write it. So my ds is going to be equal to what? Well, it's moving in a circle, so is r going to change? R d theta. So I can rewrite this as ftr d theta. And then if I want to, and I do, I can insert a sine of 90. Why can I insert the sine of 90? Yeah. Because then this is what? And in fact, I should probably, if I should switch it. Not integrating yet. I will integrate. Especially if I write it that way, because I've been trying to get you guys to write it in a certain way. What's RFT sine phi, or RF sine phi? Torque. Okay, so this is going to be equal. That is not a tau. That's going to be equal to torque. So I can say that that amount of work that's going to be done is going to be tau d theta. And now, yes, I can integrate both sides and say that the work done by some force, which of course becomes a torque, is going to be the integral from some initial theta to some final theta of tau d theta. Okay, which again is probably what you would expect it to be, because our formula for work done by perhaps a variable force was f dx. So this is going to be tau d theta. Okay, we good? All right, so power was dw dt. Remember, what was dw equal to? Yes, changing work over time. What was dw equal to? Tau d theta. Tau. And what's d theta dt going to be? Yes, omega. So power could also be written as tau omega, but you have to remember that your tau has to be constant. All right. Kind of a bookkeeping dictionary kind of day where we're just trying to get some new terms and some new formulas. All right. Everybody good? Yes? Okay, then let's do this. Let's apply this to a problem that we can do the easy way or the hard way. So let's take page 291, number 63. Casey, remind me to tell you something later. Just at the end of class, say you were going to tell me something. Oh, we could do a little, although I do some of it. I've taught a lot of different things in my life, but most abstract thing that I know. Fermi-Dirac notation is the most abstract thing that I know. And I haven't thought about that in a really long time. All right, so somebody read the problem for us, please. Okay, does everybody understand what's going on? I forgot to grab a meter stick, but we can talk about it on a miniature level, right? Pretend this is a meter stick, and it's going to fall. But we're going to assume that the part on the bottom is fixed, as if it were a what? A hinge. And what's the big global term we use for anything that looks like a hinge? A rotational axis. Okay, so that's what's going to happen. So I've got my meter stick. Here's going to be my rotational axis along the floor. Yeah, that's a little over the top. Okay, so you have a lot of skills and a lot of tools now with which to answer things. Okay, so so this is going to fall to the ground. And what are we supposed to find? Okay, so it does not specify, but I believe we are looking, oh, I guess I assumed it was the angular speed. Oh, did I? Okay, so we want to find omega f, or really vf, at 1 meter. Okay, so how are you going to do it? What? We could do it by conservation of energy. Okay, that's the easy way. We can do it the easy way. What? Oh, damn, that's the easy way. I like the hard way better because I think it tests a bunch of stuff. The hard way is work is equal to kinetic energy is equal to, it's not though. And really you have to talk about tau, it's a tau. T-A-U, actually. T-O-W would be tow. Okay, like you tow a trailer or something. Yeah. Okay, so let's try it the hard way. And then we'll see how the easy way works. Okay, so what force is causing tau? Gravitational force. Okay, so something that we need to talk about is, where does that gravitational force get applied? Not when is the gravitational force applied. Where on the object? Where? At the center of mass. Okay, so if this is a uniform meter stick, where's the center of mass? In the middle. Okay, so here's going to the center of it. So here's going to be my center of mass. And this actually applies to the conservation of energy way as well. When I'm dealing with a uniform object and I'm dealing with energy considerations, I pretend that all of the mass is concentrated at the center of mass. So if I was going to talk about the change in potential energy, it would be whatever the mass of my meter stick was times g, but my h would only be this height here, would only be half of the meter stick. Okay, so we'll come back and talk about that in a minute. Okay. Yeah, we're going to pretend that there's some kind of disturbance that lets it fall. Okay, and then we're going to ignore whatever that was. Spherical chickens. Spherical chickens. Okay, it's a joke. I'm sure if you Google spherical chickens, you'll find out what I'm talking about. All right, so here's going to be my mass M, which is the mass of the whole meter stick that's concentrated up here. Okay. It was a joke. I don't know what it is, but it's one of those, you know, a mathematician, an engineer, and a physicist walk into a bar. And there's something about how many chickens can you do something to? And I'm pretty sure it's making fun of the engineer, but it might be making fun of the physicist. But the answer is it's, you know, well, I can get 15 of them in there. Well, how do you know you can get 15 of them in there? Well, I assume they were spherical chickens. So. No idea what you're talking about. Too many distractions. Come on, focus, because I really want to finish this today. Okay, so your homework is due no matter what. All right, so here's going to be my FG. Here's going to be my R. And let's talk about what tau is going to be. What's my formula for tau? Yeah, but I don't really have those things right now. RF sine phi. Okay, so I've got my R, my F is my FG, and what's phi? So this is really going to be phi. What? Go ahead, Priya. What is it? It is. And that angle is actually theta. That angle, in this case, it does. Because phi is the angle, sorry, theta is the angle that my object has moved through. Okay, but because of alternating interior angles in this situation, theta is equal to phi. And so that's a really good thing. Okay. So I'm going to go to another slide. Everybody got what they need? Okay, so my work, which is going to be equal to my change in kinetic energy, is going to be my integral of tau d theta from some theta initial to some theta final. Well, now I'm going to substitute in for tau, so I'm going to have r fg sine theta d theta. But what are my limits of integration going to be? Well, what's my initial angle? 0. And what's my final angle? 90. Okay, so I'm going to go from 0 to 90 degrees, 0 to pi over 2 doesn't really matter. Because in this case, the angle is just an angle. It's not going to be part of angular acceleration or angular velocity. It's just an angle. Okay. So r is a constant. What does r happen to be equal to? Half a meter, 0.5 meters. Okay. What's Fg going to be equal to? Mg, whatever the mass of my ruler is. Chances are it's going to go away. And then I'm left with the integral from 0 to 90 degrees of sine theta d theta. So what's the antiderivative of sine theta? That I'm going to evaluate from 0 to 90 degrees. So I'm going to take the negative cosine of 90 degrees minus the negative cosine of 0 degrees. I have to say that for many of you, grading your calc homework was torture because you did in fact not know what the sine and cosine of pi were. So let's try it again, and I have every right to cringe when I ask this question. What is the cosine of 90 degrees? What is the cosine of 0? So those negative signs are going to cancel out, yes? Okay, so I end up with, no, I don't. So my work, which is equal to delta k, is going to be RMG. This negative sign went with this term that went away. It's okay. Okay, so that's pretty cool. And if I want to find the velocity, I know that delta k is going to be 1/2 I omega final squared minus 1/2 I omega initial squared. Thank you. What's omega initial going to be? 0, starts from rest. So if I only had the rotational inertia, I'd be all set. Okay? So I'm going to go and take a little side trip and find I. So again, here's my meter stick. Here's my axis of rotation. You open your books to table 10-2 and tell me what a meter stick looks like. No. I will never make you memorize them for a test. No, it will, hang on. Let me answer one question at a time. For the AP exam, it will be given to you, or it will be something that you are supposed to find, and they'll give it to you anyway, so that you know where you're going. So, I mean, like part 1 will be, we'll find the rotational inertia of this object. And, or it won't be that. It'll be, show the rotational inertia of this object is. What they might give you and what I might give you is like a thin rod with a disc on the end, or a thin rod with a sphere at the end, or a hoop, and give you the rotational inertia around the center of mass of a sphere and a hoop and a disc and a rod, and then ask you to find the rotational inertia of the whole object, which means you need to be able to put them together, which we did, because you just add it for the different pieces and apply the parallel axis theorem. So that shows that you learned something. The AP exam won't make you memorize that. All right. So thin rod. So remember, it's got to be perpendicular to the long way, not around a central axis. So what is it? Okay. But is my rotational axis through the center of mass? It's through one end. So what do I need to apply? Parallel axis theorem, which says I take the center of mass, rotational inertia, and add what to it? The parallel axis theorem? Yes, we just discussed how I would never ask you to memorize anything in that table. mh squared. What's h? To the center of mass. So if this is my center of mass and that's my rotational axis, that's h. Yes. Okay, so this is going to give me 1/12 m. What's L going to be in terms of R? Two R plus mr squared, which means we can probably do something with this, right? Because this is going to be 1/3 mr squared plus mr squared. Eventually we're going to do that, okay? But right now I need to know what the rotational inertia is. And I believe that is it. I could be wrong, but because it should be 4/12, and that's a third. Okay. Okay, so you with me? Okay, so I've got this, although that didn't really work. Why won't it take everything? Yeah, that was stupid. I don't know what the deal with that was. So it was RMG was equal to 1/2 I omega final squared, right? So we've got RMG 1/2. I we said was 4/3 mr squared omega f squared. And now we can do some canceling. The m's are going to cancel, which is where Priya was going. Hang on. And that's good because, again, I don't know what the mass of that meter stick was, but I don't need to. I can cancel a 2 and the 4. So, and I can cancel one of my r's. So that's going to give me G is 2/3 R omega final squared, or omega final squared is 3G over 2R. So omega final will be 3G square root 3G over 2R, or what? Keeping in mind that R is 0.5 meters. Well, no, now you got to substitute the numbers in. Okay. Okay, but I still want an answer, Priya. Oh my God. Jeez. Not radians per second squared. No, radians is right because the meters in the G and the meter and this and R are going to cancel. But remember, you're taking the square root, so it's radians per second. God, I'm going to keep teaching, but go. I'm just going to finish the problem. Okay. Well, we're just going to... So if instead of finding omega final, I wanted to know what the velocity was at the tip at 1 meter, how would I find that? I don't have to do that. Yeah, V is equal to omega final times R. Except this is a different R. Because that R, if I want to find my V final for the tip, then my R becomes what? 1 meter. So my VF is 5.4 meters per second. Okay. Yeah, now it's done. Yes, because an object only has 1 omega. If you guys want to take a break, you can take a break because we've only got one more problem to go. Okay, so last problem, and then we are done with this section. You've got the quiz on Wednesday. We will start chapter 11 on Thursday. Friday should be D-Day, and we're actually going to do lab. And it's a lab where you are actually, there are no instructions. I'm just going to tell you what I want you to figure out for me. And you're going to have to figure out how to figure it out. Okay? Which you should be able to do at this point because you know how to use all the equipment. All right, so somebody read us page 291, number 66, please. I don't care about the numbers, so just... Yeah, I got it. Don't worry, I got it. Okay, so I've got a table and the ground. I have a pulley that comes off of the table at the edge here. I think my pulley probably needs to be a little higher. I have a sphere over here that rotates. My sphere has a mass capital M and a radius capital R. My pulley has a rotational inertia capital R and a radius little r. No. They don't give you the mass because they've given you the rotational inertia. And then what I have, hang on. And then I've got a string that goes over and is attached to a mass little m. I don't care what the letters in the book are. These are my letters. We're using my letters. Okay? That's what I thought. Okay? And I believe everything starts from rest. And then the object falls a height h. So if we are to use energy considerations, tell me what's going on with energy here. What, Maddie? Energy is probably being conserved, but pick an object here and tell me what's happening to it. Maddie. Kinetic energy. So little m is going to start with a certain amount of what kind of potential energy? Gravitational. And especially if we let UG be equal to 0 down here, then all of its gravitational potential energy will be converted into kinetic energy. Is it going to be converted into its own kinetic energy only? What's it attached to, Casey? And what's that string attached to? And it goes over. And so when that mass goes down, what's going to happen to the pulley? It's going to turn. And what's going to happen to the sphere? It's going to turn. And if things are in motion, then they have what kind of energy? Kinetic energy. So that gravitational potential energy of little mg is going to become the kinetic energy of little mg, of the sphere, I'm sorry, of the pulley and of the sphere. So when it hits the bottom, it's not going to be going as fast as if I just dropped it a height h, because it's going to have to spread that potential energy over 3 objects. Okay, you with me? All right, so like we said though, as Maddie said, the kinetic energy is going to be conserved. And I've only got gravitational potential energy and kinetic energy in this problem. Everything starts from rest, so there's no initial kinetic energy. It means there's no, well, yes, with the caveat. Okay, I am in fact going to make that be equal to 0, because the potential energy of the mass will be 0. The potential energy of the pulley and the sphere will not have changed. They will have the same amount of potential energy as they do initially as they do finally. And they only have potential energy because there's some distance above where I set the gravitational potential energy to be equal to 0. Okay? So, I'm sorry, say it again? Yes, because they'd be the same on both sides of the equation, and I would just cancel them out. Exactly. Okay? So, what is my gravitational potential energy? mgh. And then I've got a whole bunch of things that have kinetic energy. The mass has kinetic energy, the pulley has kinetic energy, and the spherical shell has kinetic energy. Okay, and I'm just going to take this and move it, or copy it to the next page, okay? There we go. Okay, so I've got my mgh. What's my formula for kinetic energy for that mass? Maddie. They don't change. Yeah, because it would be the same on this side of the equation as it would be on this side, so they would cancel. Okay, so the pulley is rotating. How do I write rotational kinetic energy? Okay, and I'm going to call it omega pulley. And then I'm going to have a similar expression for the spherical shell. I'm sure we could figure it out, but not now. Okay, so I've got 1/2 mv squared Now, they told me what the rotational inertia of the pulley is, right? And it's just I. But what's the rotational inertia of a spherical shell? Okay, so 2/3 capital M capital R squared. So this is kind of cool. I know all of this. I know that. I know that. I know that. I'm looking for that, the V. But I have two other things that I don't know. I don't know omega P. I don't know the rotational velocities for the pulley or the sphere. So what am I going to do? So what do you think? Yeah, we can look at V equals omega R. Say it again. This entire system will have the same tangential velocity because the string can only have one velocity. It is, yes. Well, no, V in here is, let's go back to the picture. V is the mass, V is the speed of the mass. Therefore, because it is attached to the string, it is the speed of the string. Because the string goes over the outside of the pulley, it is the tangential velocity of the pulley at the outer edge. And because the string goes around the spherical shell, it is also the tangential velocity at the outside diameter of the spherical shell. Okay? But it's because that string can only have one speed. And so they're all connected. Okay? So VP is going to be omega P times little r, right? Because that's the radius of the pulley is little r. And actually, that's going to be equal to V, but I want you to know it's for the pulley. Okay. For the shell, it's going to be omega S times what? Capital R, because that's the radius of the thin spherical shell, and I want to go out that far. So once again, I can rewrite my energy equation here. So I've got mgh 1/2 mv squared plus 1/2 I, but omega p is going to be v squared over little r squared, right? Plus, make sure everybody's paying attention. I'm going to cancel my 2's up there, right? So I'm going to have 1/3 capital M, and then I've got r squared omega s squared, which is going to be equal to v squared. And the v's are all the same. Okay. So all you're really doing is solving for v. So of course, we're going to pull out a v squared. And we've got m over 2 plus I over 2r squared plus m over 3. And then I'm just going to divide both sides by that monster. and then take the square root of both sides. And it's pretty ugly, and they give you numbers, and you could substitute the numbers in, but I don't know what the answer is, and I don't really care. It's more that I want you to understand how the problem works. Okay, so that's it.